Okay, good evening, ladies and gentlemen, and let me bid you a very warm welcome to the Royal Society. My name is Peter Bruce. I'm the Physical Secretary and one of the Vice Presidents here, so it's really wonderful to see so many people attending this Kavli lecture this evening. The Royal Society was founded in 1600 with a royal charter from Charles II, and such luminaries as Robert Boyle and Christopher Wren were the founders. And we've been, throughout our time, all about excellence in science and engineering. And of course, we're rewarding excellence this evening with the Kavli Award to Ed Hawkins. But we don't just reward excellence in science. We also have an important role as scientists in providing objective evidence and advice to governments. And of course, the topic of this evening's lecture of climate change speaks very much to that agenda, because we need rigorous science to understand climate change, but we also need to present objective evidence to decision makers and policy makers about what they need to do about this. And we were just talking a few minutes ago, Ed and I, as we were having a cup of tea, and reminding ourselves that back in, it was actually Arrhenius, of course, and chemists know Arrhenius for the rate constant and the rate of reactions, back in the late 1800s, that predicted this problem would be here, and we've revisited that prediction many times over the succeeding years, and still we don't seem to be getting it in some quarters. There we are. Anyway, the Kavli Medal and Lecture is awarded annually for excellence in the fields of science and engineering related to the environment and energy. Ed is a climate scientist at the National Centre for Atmospheric Science in Reading. He is particularly interested in gathering data on the weather back from in the early industrial times, and then using those data along with modern models of weather to understand the links between climate change and weather. He's also, again, speaking to our policy agenda, involved in the Intergovernmental Panel on Climate Change reports, and one that will come out quite soon. So without further ado, I don't want to take any more of his time up. Let me invite Ed to come and give his lecture.
So thank you very much, Peter. Thank you all for coming. It's a wonderful privilege to be standing up here. I'd like to thank the Royal Society for giving me this opportunity to talk to you all this evening. So it's been a big couple of weeks for climate science and discussion of climate in the media. I'm sure you're all aware of all of the discussions about the protests here in London and around the country, and indeed around the world, as well as the school strikes happening all over the world, inspired by the Swedish schoolgirl Greta Thunberg, who visited the UK last week as well. And I think this has really sparked a conversation amongst the public about climate change, what we're going to do about it, and I'm hoping we can continue that conversation this evening. So I'm going to talk a little bit about the changes that we've seen to our climate and to our weather, and talk a little bit about what that means for the future, and the choices that we have to make going forward from here. So, but I'm going to start our conversation this evening by visiting Greenland. So my wife and I were lucky enough to visit Greenland a couple of summers ago on a kayaking expedition through the Greenland fjords. And this photograph is from that expedition that we took. So we were kayaking through the fjords, seeing the icebergs, and then towards the end of the expedition, we reached the glacier front. And we were able to sit on this little tiny rocky island and just sit and watch the glacier and listen to its sounds, groaning and creaking and cracking as glaciers tend to do. It's utterly spellbinding, and I'd recommend it for everybody. But I turned to our guide after sitting on this island for a while and said, he'd been guiding to the same spot for several years. And I said, have you seen any changes during those few years that you've been guiding here? And he took out his mobile phone and showed me some photographs, which I'm now going to share with you this evening. So this was the photograph he took of that glacier in 2014, when on his first expedition to this glacier front. And if you can just keep your eye on the lump of rock in the middle, towards the middle right, that rock's going to be in all of the photographs. So you get a sense of scale and a sense of the changes that I'm going to show. So that was summer 2014. The following year, 2015, there's clearly been quite a retreat of the ice, the glacier, in front of that giant lump of rock. 2016, again, the glacier has moved a lot further back. And this is the photograph that we were able to take in 2017. So in that time, we've seen the glacier retreat by a couple of 100 meters over just a few years. So the natural world is telling us that something is happening. The natural world is telling us that the world is warming up, and this is resulting in retreat of this particular glacier. And we're able to, so the little island we're sitting on is in the bottom right-hand side of that photograph. And that was the first year they're able to sit on that island and just sit and watch the glacier. It had been uncovered over the previous year. The changes are very, very rapid. But it's not just this particular glacier. All across Greenland, we're seeing glaciers melt. Recent data from satellites and measuring the gravity and the mass of Greenland has allowed us to estimate that Greenland has recently been losing mass at the rate of 4 litres per person per hour. So each and every one of us, we're effectively pouring 4 litres worth of water or ice into the sea every hour. Or in more sort of traditional units, 3 Olympic-sized swimming pools per second. So this is an awful lot of water which is coming off Greenland into the sea and causing sea levels to rise. But it's not just in Greenland that we're seeing these changes. We have some beautiful old sketches and photographs of glaciers across Europe. This one is a sketch of the Pasteur Glacier in Austria in 1885. And there's a handy person for scale, so you can see the scale and the person sitting in the bottom right-hand side. So if you visit the same glacier today, you see photographs like this. The valley is now empty of ice. And you can see where the glacier was in 1995. It has retreated a long way in the time since 1995. And then you can walk further down the valley, and you can see again the changes that have been happening, even again, just over a few years. That was where the glacier front was in 2015. So these changes are happening really rather rapidly, and they're happening all over the world. So again, the natural world is telling us that something is going on, that the world is warming up. So all this water being melted from the glaciers on Greenland and across the land glaciers in Antarctica is all ending up in the ocean. The oceans are warming and also expanding, and so this is causing sea level to rise. And again, we have records of sea level going back about 130 years, and so we can watch how the sea levels have risen over that time, slowly at first, and then gradually towards the end, accelerating. So eventually we reach over 20 centimetres, 24 centimetres of sea level rise since 1880. So we can again see the effects. The natural world is telling us that something is going on. The oceans are warming and the glaciers are melting and adding that water to the sea. We also have long records of what's going on in the Arctic. We have satellites which have measured the sea ice in the Arctic since the late 1970s. And again, we've watched the satellite data come in and we've watched the sea ice retreat. It's lost about a third of the summer sea ice over the last 40 years or so. There's lots of variation from year to year, but over time the amount of sea ice in the Arctic has dropped. So now we're seeing shipping traffic able to navigate through the Arctic in summer to shorten the journeys between Asia and Europe, taking shortcuts across the pole rather than going round the long route. So again, it's the natural world telling us that something is happening. So let me just watch that once more. So you can see that the very white concentrations, the very sort of old, thick ice, again, melting away until, eventually we will see very little sea ice in summer over the next 30 years or so. We suspect there'll be very little sea ice there in the summer. So the question is now then is, why are these changes happening? We're seeing all these changes over a century or so. Do we understand why they're happening? So I'm briefly going to talk a little bit about the history of that understanding. How long have we understood what's causing all of these changes? So I'm going to talk a little bit about two characters from the history of climate science. Talk about John Tyndall on the left and Guy Callendar on the right, both working in London when they did this research. So John Tyndall is famous for essentially quantifying for the first time the greenhouse effect. So in 1861, he performed a set of experiments to understand the properties of various different gases. So he had this apparatus. You can still see some of this apparatus in the Royal Institution in London. It still exists. So he set up this apparatus. We had two heat sources at different ends of a wooden tube. And he was able to fill that tube with different gases and measure how much infrared radiation or heat different gases absorbed. And he was able to do that by a temperature gauge in the middle between these two heat sources. And so a series of very careful experiments, he determined that gases such as carbon dioxide and methane absorbed infrared radiation and heat. And that is the fundamental physics behind the greenhouse effect as we understand it. And so all the way back in 1861, we understood the basic physics, which means that if we increase the levels of those gases in the atmosphere, they will absorb more of the infrared radiation which is emitted by the Earth and act as a blanket, and that therefore the Earth will warm. And Tyndall said in 1861 that if we change the concentrations of these gases in the atmosphere, the climate will change. That's how long we've understood the basic physics and chemistry of what was going on in our atmosphere. So what did they do with this piece of information? Well, a little bit later on, as Peter described, we had Svante Arrhenius, who was a Swedish a chemist, who was actually an ancestor of Greta Thunberg, as it turns out. But he worked out that in the 1890s, that if we increased the levels of carbon dioxide in the atmosphere, he made a prediction about how much the planet would warm. But he said it would take a very long time, because they didn't foresee how quickly the Industrial Revolution would happen, how quickly we would start burning coal and producing carbon dioxide and putting it in the atmosphere. And it took until the 1930s, until Guy Callendar, an English engineer, who was the person to put all these pieces together. We had observations of temperature change from various locations around the world. We had this prediction from the 1890s that if you increase the levels of carbon dioxide in the atmosphere, the temperatures will rise. So Callendar was the first person to determine how much has the carbon dioxide levels in the atmosphere changed, and they changed by quite a lot at this point. He was also then able to piece together temperature records gathered from around the world, doing all the calculations by hand, no computers, and draw these hand-drawn graphs back in the 1930s, demonstrating that the Earth's land areas had warmed by about 0.3 degrees over the preceding 50 years. So here we have the first evidence that the world was warming up in 1938. But even more importantly, at the top right-hand side of his graph is a little dashed line labeled CO2 effect. So from the observations he had taken of the amounts of carbon dioxide and how it increased in the atmosphere, he was able to make a prediction of how much that should have raised global temperatures. And it was about half what he saw. So back then in the 1930s, we had a prediction of how much the planet should warm due to the increase in carbon dioxide, and we'd seen that temperature rise. Again, we understood the basics over 80 years ago. So what's happened since? So we have pretty good global temperature records since 1850, up until, so this particular graphic shows the data up until the end of last year. And so these are the warming stripes. So each stripe shows the temperature in one particular year, from 1850 on the left to 2018 on the right. And they're color-coded for the temperature in that particular year. And so you can see from 1850, we see blue colors, colder temperatures. As we progress through, we see some colder years in the 1880s and 1890s. A series of volcanic eruptions had cooled the climate at that time. And then we see gradually some warming start to occur in the 30s and the 40s that Callendar had seen. A period of sort of relatively stable temperatures in the 50s and 60s. And then from the 1980s onwards, a rather rapid increase in temperatures across the globe as we're seeing this transformation from blues to reds. So again, our temperature records leave us in no doubt that the planet has warmed, just like the natural world is telling us is going on. So all the data is telling us that the world is warming up. So this global picture is built up of temperature measurements from across the world. So I'm going to focus a little bit now on the UK, where we are now. So we have long records from single locations across the UK. So I've picked out 5 examples here. From the north of Scotland in Stornoway, Northern Ireland, Armagh, north of England, Durham and Sheffield, down to Oxford. And they all show a very similar picture. We're seeing warming at all of these sites, independent measurements taken completely disparate ends of the country. Warming of 1.3, 1.4, 1.5 degrees across all of these different locations. And not only the trends are very similar, but the variations from year to year are also very similar. Again, giving us confidence, these independent measurements showing us the same thing across the country. So we've seen a long-term trend in UK temperatures. So what's happening globally is being felt where we are here in the UK. We live on one planet. So let's just dig into Oxford a little bit more, because Oxford is one of the longest records that we have. We have records since 1814. So every single day at the Radcliffe Observatory in Oxford, someone has gone outside and taken the temperature. Every single day since 1814. And we have those records stored in handwritten logbooks in Oxford. And we've those logbooks have been gone through and the temperatures have been taken out. And now we have that data available to us. And so again, it's the same stripes going from 1814 on the left, 2018 on the right. So at the scale of a single weather station in the centre of Oxford, we can see this warming trend, which is unmistakable. There are some very interesting ups and downs. Again, we see periods of colder temperatures in the 1830s, 1880s, possibly again due to those volcanic eruptions that we know happened at that time. But again, the warming trend is unmistakable. So let's have another closer look at Oxford again. So this is the actual temperature. So rather than the visual impression given by those stripes, here are the actual temperatures measured in Oxford. So the annual temperatures back in the 1850s or so was between 9.5 and 10 degrees. That was a typical year. Now we're seeing temperatures 11.5 degrees measured for the annual average in Oxford. But what I'm going to do now is add on the global trend to this particular graph. So what's happened globally compared to this very, very local data. So in Oxford, the temperatures have risen about 60% faster than the global average. So that's where many people may live in this room, perhaps, I don't know. But that's what the data is showing us, that the data in Oxford shows 6% warmer than the global average. But not only that, the pattern of warming throughout the last 2 centuries is essentially identical. The red line, the global picture, essentially looks like a smooth version of the Oxford data. The same picture is being told from the scale of a single weather station in the centre of England as it's being seen on the global stage. Again, we live on one planet. We're seeing the fingerprints of global warming at the very, very local scale. So one more way of looking at the temperature change. Some of you may have seen this graphic before. It's the temperature spiral. Again, this is showing global temperatures and how they've changed since 1850. So you see the months of the year around the edge of the spiral, and you see the counter in the middle showing the years as they progress. And what you see is that as the temperature rises, time goes on, temperature rises, and the spiral gets bigger and bigger. And you'll notice there are some red lines on this particular graphic, denoting 1.5 and 2 degrees above pre-industrial levels. These are the levels set by the United Nations Paris Agreement as the temperatures that we would like to avoid crossing. So we can see that the rise of temperature relative to that important pre-industrial baseline and how warm the temperatures have got. So some months have got rather close to that 1.5 degrees. That doesn't mean that we're about to cross that threshold. That threshold is about having a long-term global average across a whole set of years. But again, it shows us how temperatures are warming, how close we're getting towards these temperature thresholds, which we would like to try and avoid crossing. So as temperatures rise, this gives rise to all kinds of risks for the future. And there's a whole set of risks listed on this particular slide. So we of course have risks from heat waves. as temperatures go up, we expect to see more heat waves, more floods, more droughts, wildfires. We've already seen sea level rise and glacier loss. Not every country or every place will experience all of these risks. They may be isolated in certain locations, but all of these risks will be experienced somewhere on the globe as temperatures continue to warm. So the question is, what do we do about when we see these risks? What actions are we going to take in response to these risks that some of these we're seeing already, and some of these are projected to happen in the future. So in 2015, the United Nations came together and wrote the Paris Agreement. So all the nations of the world at the time signed up to that agreement, which aims to avoid the worst of those risks by cutting global CO2 emissions to net zero during the 21st century. So it's not just reducing emissions, it's cutting them to net zero. It's not just dabbling at the edges. We have to remove all the sources of carbon dioxide from all of our factories, our energy generation, and all of our personal behaviours. All of that generates carbon dioxide. They have to be cut to net zero, which means that we have to remove from the atmosphere as much carbon dioxide as we emit. And we don't know how to remove carbon dioxide very easily, which means we need to cut the emissions side really rather dramatically if we're to avoid reaching those targets. And this will require a complete transformation of society. We need to completely revolutionise our energy generation, our industry, our infrastructure, and our personal behaviours. It is really a very, very difficult challenge to decarbonise the global economy. And that leaves us with some very difficult choices. This is not easy. There's no magic bullet to solve this problem. It's going to rely on international agreements. We've got some very difficult choices to make about how we travel, how we generate electricity, how we generate heat, how are we going to heat our homes without using gas. Now, that transformation does not take place very quickly. What food are we going to eat? How much do we waste? What do we do with our waste? What are we going to do about global poverty? Are there going to be any trade-offs that we have to make? What are we going to use our land surface for? Are we going to use it for growing crops, for growing forests, which can remove carbon dioxide? Or do we need to use our land area for growing crops which we can later produce energy with? These are very, very difficult decisions which there's going to need to be a very large international agreement on how we tackle this problem. But the other side of these choices is that further warming will be inevitable. We will continue to emit carbon dioxide for a decade or two or three or four, and that will continue to warm the atmosphere. So we will also need to adapt to the changes that are going to occur. So the mitigation, the reduction of carbon dioxide emissions is one side, adaptation is the other side. So what might we have to adapt to? So again, I'm now going to give a few UK examples of this type of thing that we might have to adapt to. So we all remember, I'm sure, last summer's heat wave. Really rather hot at certain times, rather dry, caused a few problems on the roads, on the railways. Outdoor electronics was another thing that suffers during the heat. We have to think about how we deal with things like sensitive electronics, which has to be outdoors, for example. So there's a lot of discussion about 1976 and 2018. So 1976 and 2018 were roughly the same temperature across the country. We see this map, 2 degrees warmer than the normal summer, for example, in both those summers. So what does that tell us? We've had all these heat waves before. What are we worrying about? So I think it's worth thinking about the bigger picture about what happened in 1976 and in 2018. So let's zoom out from our UK-centric perspective and see what happened across the rest of Europe. So what we see actually in 2018, UK was not the hottest place. We saw very large temperature changes over Denmark, Sweden, France, and other areas. We saw the largest the warmest anomalies, the warmest hot temperatures in other parts of the continent. So, the UK and France were kind of standout examples of where the heat was in 1976. So even though the temperatures in the UK were rather similar, they're even hotter elsewhere this last summer. But let's zoom out again and see the global picture. In 1976, again, the UK and France were, essentially the one isolated red spot over the land areas, whereas last summer was warm over a large fraction of the globe, over the land areas. So, the UK was not particularly unusual. In fact, it was relatively cold compared to some other places in terms of how much warmer than usual it was. We saw giant heat waves over large parts of the Northern Hemisphere. So looking in one place isn't necessarily representative of what's going on globally. It's this global picture of increased heat happening all over the world. But coming back to the UK, what might we expect? So we have some choices to make about the future. We have a choice of different pathways that we might follow for the future. So this is global temperature. We've warmed by about 1 degree centigrade already, just over 1 degree. And these choices that we make now about our emissions will dictate whether we follow a pathway leading us to 1.5 or 2 degrees, which are the United Nations target temperatures, or whether we exceed those temperatures and go to 3 or even 4 degrees warmer than pre-industrial times. Those are the choices we have to make. So what would happen under these different, 4 imaginary pathways that we might follow for the future? Which one are we going to choose? And what does that mean for summer temperatures in England? So England summers tend to be 15 or 16 degrees, roughly, on average. Last year was about 17 degrees. Again, England summers have followed the global pattern of warming 40% faster than the global average, which means that over the next 80 or so years, again, we will see temperatures in England in the summertime warm by 40% more than the global average. If we make that assumption that what's held in the past holds in the future, those are the types of trajectories that we will follow. So what does that mean for experiencing a summer like last summer, like 2018? How often are we going to get that type of heat? So at the moment, we might expect a summer like 2018 roughly once every 15 years or so. So it's quite unusual to have last summer being as hot, 1 year in 15. If we follow a 1.5 degree pathway, that will end up being 1 in 4 summers like last summer. If we follow a 2 degree pathway, last summer will become completely normal. We'll have that type of summer every other summer. If we follow a 3 degree pathway, a summer like last summer will become a cold summer by the end of the century. We will very rarely have a summer as cold as last year if we follow a 3 degree pathway. If we follow a 4 degree pathway, that happens even earlier. Again, we will hardly ever see a summer as cold as last summer happening at the end of the century in that type of world. So it's all about risks. If your industry, your business, your buildings are going to struggle in the heat, then this is the type of event that's going to become more frequent. It's going to become normal. What is abnormal will become normal. And it may even become very, very cold. That particular summer would appear very, very cold. So if you're building the next generation infrastructure, roads or railways or mobile phone networks, this is the type of information you need to make informed decisions about what temperatures you're going to need to plan for. And so we potentially need to revisit some of our infrastructure choices, given the temperature rises that we're expecting to see. Flooding. I'm sure many of us remember the flooding in Somerset Levels in 2014. Hundreds, thousands of people flooded homes, causing a lot of disruption and misery. So what can we say about flooding? So if we think about 2014, it was caused by a whole series of storms coming across the Atlantic in a typical winter storms. They happened to dump their rain all in one place repeatedly. So we had a lot of rain all in one place, which caused the flooding. So what can we say about how climate change has affected that event? So the storms were not particularly unusual. But in a warmer world, a warmer atmosphere can hold more moisture. So the atmosphere can hold more water. There's more evaporation from the oceans. The atmosphere holds more water, which means when it rains hard, we get more rain. And so these storms almost certainly produce more rain than would otherwise have happened in a cooler world. So we had more rain because of climate change. But the rivers that the rain would normally drain in drains to the sea. And we've also seen sea level rise, which means the rivers cannot drain quite so efficiently into the sea. So again, because sea levels have risen, kept more water on the land, increased the risk of flooding. So climate change has not necessarily changed the chance of getting some of these events, but it has made it worse. And flooding is one of the examples where we expect to see more risk of heavy rainfall in the future, with higher risks of flooding over the UK, purely because a warmer atmosphere can hold more moisture, therefore more heavy rainfall. And those are kind of the easier things that we like to think about for risks for the UK in future. Heat waves, it's going to get warmer, more frequent heat waves. Flooding, warmer atmosphere holds more moisture, more heavy rainfall. That's the easy part. The much harder part is what might happen to our weather. How might the weather patterns change for the UK and around the world? So this is October 2017. This is the view of the planet from space. The EUMETSAT satellites continually monitor the planet, and they produce these lovely animations of the world's weather. And I think you stare at these for hours, just seeing the storms flowing around the southern hemisphere, the storms flying across the Atlantic to hit the UK, dropping a lot of rain. You can see the tropics, the bubbling of convection and clouds in the tropics. And October is hurricane and typhoon season. So you see some of these hurricanes and typhoons crossing the Pacific and the Atlantic. And at this time we see Hurricane Ophelia. Some of you may remember Hurricane Ophelia, ex-Hurricane Ophelia, when it hit Ireland in October 2017, caused a lot of damage. So the question we might like to think about if we're trying to adapt to the future is, how are the weather patterns going to change? Are we going to see these storms, the track of these storms, move further north or move further south? Are intense storms become more frequent or less frequent? If we want to adapt to a future, we need to answer these types of questions. And these are much harder questions to answer. So how might storms such as that happened 30 years earlier from that satellite animation, October 1987? Some of you may remember this as the Michael Fish hurricane that caused a lot of damage across swathes of England, ripping up lots of trees. So how might storms like this change in the future? Well, these happen relatively rarely. So what we really need is a much longer record of these types of storms to understand how they might have changed. We need much longer records of how the weather has varied hour by hour, day by day, if we're going to try and determine what's happened to the storms. Are they moving north or moving south? Have they already moved in those directions? Can we see those changes already? So this wasn't the first such storm that we had. So we're going to go back in time now and visit 1903. A bit of a similar picture in 1903. A storm in February 1903 ripped up 3,000 trees in one park in Dublin. And this is where that photograph is from. The storm continued across the UK and caused a whole swathe of damage. So again, this is a storm, very severe storm that we have to think about. We need much longer records of these types of events if we're to understand how they occur, where they come from, how might they change, how have they changed already. So what can we learn about this storm now? Can we go back and what can we learn about that storm today? So the Met Office, they had a weather chart from the 27th of February 1903. They were taking observations. They were able to draw this chart on the morning of the storm. The observations were telegraphed from across the country into London, and they were able to draw this weather map, this synoptic chart. And you can see the low pressure, the storm over the central Scotland. The isobars packed very closely together, as you might hear the weather forecaster say. High winds where you see the isobars, the lines of pressure, very close together. High winds over Ireland and northern England. So the Met Office were able to draw this chart because the data was sent to them from all over the country and all over Europe and they were able to collect that data and draw the chart. And we also have a map of the damages caused by this storm. It was so severe that the Royal Meteorological Society at the time commissioned a special report to understand the storm, where it had gone, the damage that it had caused, and so on. So this is a map from that report in 1903 after the event, showing where the damage had occurred across Ireland and northern England. So every little symbol is either some trees being uprooted or some structural damage or some fatalities, some ships being sunk. So we have a map of the damages. We can try and learn a lot more about this event. So what happens if we go back and try and learn more about this event? We know there are lots of observations taken. Can we map out this event in great detail now using our modern technology, using our modern weather forecast models? Can we go back and pretend to make forecasts of this storm using the data that was available at the time? And that's what we're trying to do. But there's a problem. If we go to our databases and ask the databases, give me all of the pressure observations from February 1903 so we can map out this storm, the map is rather blank. Where is the data? You can see data in some countries, Germany and Switzerland, lots of data, not a single observation over England or Wales in our databases. So where's the data gone? There's a few scattered observations over Ireland and Scotland, not much over France or Spain. In fact, even got more observations from Libya than from England. So where is the data? So we're going to start our search for this data in perhaps a rather unusual location. We're going to go to the top of Ben Nevis. It's not the most obvious place you would start to look, perhaps. Ben Nevis Mountain, the highest point in the UK, 1,345 metres above sea level. So if you climbed Ben Nevis in 1903, you would have found a hut at the top, a rather large hut. And there may have been someone standing on the roof. So you can see this photograph was taken in winter. You can see all the ice and the rime and the snow on this particular hut. And you might wonder why it was there. Why was there a giant hut on the top of Ben Nevis? There was an observatory, a meteorological observatory at the summit of Ben Nevis between 1883 and 1904. So if you climbed the mountain and walked inside the hut, you probably would have met one of these three gentlemen, the weathermen of Ben Nevis. And they lived at the summit of Ben Nevis for 20 years, winter and summer. And they took a lot of very detailed weather observations. Every single hour, night and day, winter and summer, one of them would step outside their hut and go and take the regular weather observations of pressure and rainfall and temperature and wind and sunshine during the day and cloudiness. They'd record it all in very faithful detail every single hour. Completely isolated during the winter time. Three of them would live there essentially on their own for 9 months of the year with canned food. A truly remarkable achievement. These were sort of pioneers. They were, while their contemporaries were off exploring the Antarctic, exploring the Antarctic and exploring the Arctic, the weathermen of Ben Nevis were exploring the atmosphere. They were living as high up as they could in the UK, the coldest, wettest place in the country, just to take weather observations. Now, most of the time, they lived inside a cloud. If anyone here has climbed Ben Nevis, you'll know that more often than not, it is completely cloudy at the summit. But every now and again, they would get these beautiful views and take these lovely photographs of the views across the mountains and the valleys beyond. Or even take photographs of snowstorms crossing the mountains nearby. So what happened to all their data? It wasn't on our map. It only exists in the form of photographs of the observations. They were published soon after the observatory shut in 1904, and there they've stayed ever since. So we have images of these very detailed observations. This happens to be the observations from the barometer of pressure for February 1903, when that storm occurred. There are 2,000 pages like this in their logbooks, 1.5 million hourly observations of temperature, pressure, wind, and rainfall. So how are we going to gather this data and turn it into more useful data, which we can actually use to help understand the weather a bit more? So I approached a couple of PhD students. How would you like to create a unique data set? Fantastic. You have to type in 1.5 million numbers into a lot of spreadsheets. There was less enthusiasm at that point. So it's a great story, you know, these people living at the top of the mountain. And so we decided to ask the public to see if they could help us. And so we set up a website, weatherrescue.org, and 3,500 people stepped forward. It took them just 3 months to type in all that data. 1.5 million observations, several person years of effort, crowdsourced to 3,500 people. So we managed to digitize this data much faster, much more cheaply, and much more efficiently than asking someone else, a PhD student to do it, for example. And it got people involved in learning about, you know, the weathermen of Ben Nevis, learning about the weather. How do we observe the weather? So they learned science while doing this as well. And this is only possible because of an organisation called the Zooniverse, who provide the platform to allow these types of projects to be built for free. So very efficient way of getting the public involved in doing science. And there's any number of these citizen science projects that you can get involved with. We've run this one very successfully so far. As I said, rescued these 1.5 million observations. So at the end of those 3 months, I asked our volunteers, you know, are you bored yet? You know, would you like to keep going? And I was rather surprised when they say, yes, we want to keep going. We want to do more. So we went, right, what do we do next? So we have a very detailed record now from one location, hourly observations from this one location. What we need is the bigger picture. And so again, we turn to the Met Office, and they have what's called their daily weather report. So every single day since the 1860s, the Met Office has produced a daily weather report with handwritten observations telegraphed to London from across Europe. So this is the one page from February the 27th, 1903, the day of the storm in Ireland. So we have observations from Scandinavia, from the British Isles, from across mainland Europe as well. But they're only handwritten. We do not have the digital copies to use them. So again, we asked the volunteers, can you help us? And so they said yes. And so over the next 6 months, we managed to rescue another 1.8 million observations from over 50 locations across Europe for the 1900 to 1910 period. So including the data for this particular case study storm. I said, you know, are you bored yet? And again, the answer was no, give us more. And so if you visit weatherrescue.org today, the volunteers are currently rescuing data from the 1860s and the 1870s. Is anyone here one of our volunteers? A couple here. Thank you very much. A very public thank you. Giving up your spare time to help climate science is wonderful. So what has this helped us do? So we come back to our map of pressure observations, which was rather empty before. It's now a bit more filled in. We have all the black dots represent individual observations for the day of the storm. So we now have observations across the UK, across France and Germany and Scandinavia, and even in the Azores. So what does that help us do about this particular storm? So what we can do with that data is go back to 1903, take that data and put it inside a modern weather forecast model and do a short-term weather forecast for that particular event, only using the data that we had available at the time. It's called a reanalysis. Before we had this new data, the storm looked like what we see on the left-hand side. We see a bit of a storm, low pressures, and the green colours represent the confidence in our estimation of where that storm was, how deep it was. And it's a bit hazy. It's very uncertain about where the storm was, how deep it was, the damage that it caused, the winds, for example. The storm, as simulated here, it doesn't have strong enough winds to uproot all those trees in Dublin. If we add in all of our new observations rescued by our volunteers, we come with the right-hand side. We can recreate that storm to far more fidelity, far more accurate, and actually now we see the isobars much closer together, producing the winds that can uproot trees in the right locations where we know the damage occurred. So we can be very confident now that we can simulate the storm in far greater detail than ever before. Of course, this is one example. You know, I've used this storm as an example. This goes for the whole period that we've rescued the data for. We can map out the weather hour by hour in far greater detail than ever before for this period that we have the data for. So here's the storm hour by hour in February 1903 crossing Ireland, crossing Scotland. We can now watch its progression across the country in far greater detail than ever before. We can see where the winds were strongest by the tightly packed isobars in the right locations where we know the damage occurred. But can we do better? You know, the picture that I showed just now is still a bit fuzzy. We're still not entirely confident. So let's go back to the archives. We know that observations were taken at all of the red dots as well. We have the images of the logbooks of those observations everywhere where there's a red dot. And that probably doubles the amount of observations we have now. So if we put a bit more effort in, we could rescue all of those observations as well, and again, map out the weather in much greater detail than we could before. So that's the next step of our journey, is to try and rescue all of that data as well for a much longer period and map out the weather so we can understand how these storms are changing. How is the rainfall that comes from those storms changing? Are we getting more rainfall from the storms compared to those that happened over 100 years ago? So that's the next challenge. We want to try and answer questions like, how wet could a month be? Can we, you know, how high do we need to build our flood defences? We can go back to 1903, which is October 1903, the wettest month in UK history. Try and understand, why was it so wet? Where did the storms come from? How would those storms look today? How much more wetter would it be? How much more flooding might we get? So there are huge UK archives of undigitised meteorological data. Conservatively, 1 billion observations tied up in the archives from ships, from land. And I had a lovely tour of the archives here earlier today. We found observations from all over the world, from Melbourne, from Calcutta, from Madras, from all across the UK, tucked away in the archives downstairs. Again, none of these have ever been looked at, let alone rescued or digitised or used. We have data back to the 1700s, maybe even the 1600s, tucked away downstairs here, and actually in other archives around the country that we've never looked at. And all of these observations will help us map out the weather, map out how temperatures have changed, how has rainfall changed. And we're not making the most of them, unfortunately. But that's where our volunteers have come in and helped us on the first step of this journey. It's a very long journey that we're going to undertake. So recovering these observations would improve our understanding of extreme weather, such as this storm, but that's one example, and help inform adaptation decisions that we're going to have to make. But the amount of adaptation that we're going to have to do depends on our future greenhouse gas emissions. How warm is it going to get? We have choices to make about how warm the world will get, and those are our choices to make. And those choices are crucial now to determine which of those pathways we follow. Do we follow a 1.5 or 2 degree pathway consistent with the Paris agreements, or do we continue to emit a loss of carbon dioxide and we follow one of the higher pathways with greater risks? And those choices are ours to make. Thank you.
Well, thank you very much, Ed, for a very stimulating lecture, maybe also a salutary one, actually, it should be said. So we have time for a few questions. So if you'd like to raise your hand and just wait for the microphone to get to you. And when it does, please say who you are and any affiliation you have. I think I saw a hand somewhere here. Okay, there's one here and one here. Okay. Please.
Thank you, Ed. Fascinating talk. It's Leo Hickman from Carbon Brief website. You touched on, you know, from Guy Callender onwards, the huge journey climate science has been on. If you had a nominal pot of 10 million, 100 million, what would you focus the research on? So we know there's a few known unknowns within climate science. Where would you, if you had the decision to make, where would you focus that research money now?
That's an excellent question. If I'm not trying not be biased, so I would certainly try and make more use of these historical records. I think that's vital. The UK has probably one of the largest undigitised archives anywhere in the world. But other than that, I think we still need to know more about clouds. I think that's a big area that we have to think about. How are clouds going to change in future? That kind of is one big key question which we have to worry about, because we have choices to make about our emissions, but there's then uncertainty about how much warming those emissions will cause. And a large part of that uncertainty is due to what has happened with clouds in the future. We have to understand, I think, where there might be some thresholds in the system. What temperature might we commit to losing Greenland, for example? There's 7 meters of sea level tied up on Greenland, and at some point we'll reach a temperature where we'll commit to losing Greenland. 7 meters of sea level rise. It will take centuries for that sea level rise to occur, but we could commit ourselves to that happening at 1.5 or 2 degrees potentially. So that is a big issue which we need to try and understand. Where are those thresholds that we might want to try and avoid really rather seriously? Hopefully that helps.
There's a question over here, and then a couple at the back, but we'll take this one first.
Hi, thank you. This might be a bit controversial, but what can you say about climate change and animal agriculture, if that's anything you can speak?
Animal agriculture?
Yeah, if you can speak about that.
Okay. So agriculture in general and animal agriculture is obviously a source of greenhouse gas emissions, methane particularly. And so we have some very difficult decisions to make about agriculture. And the emissions reductions from agriculture are really rather difficult. So agriculture is one of the areas where we are likely to have to balance the emissions that come from agriculture with negative emissions, or somehow removing greenhouse gases from the atmosphere. We might need to make some very difficult choices about what food we eat, and the Intergovernmental Panel on Climate Change report said that essentially one of the things we could do is eat less meat, particularly cows and sheep, because they produce a lot of methane. And often what we see is that where trees are being chopped down in the tropics and the deforestation is occurring to grow food for cattle. And so, again, we're seeing destruction of rainforests to grow food for cattle, as well as for grazing cattle. So that is a major source of greenhouse gas emissions, and it's one of the things that we could all do if we wanted to help this problem is by cutting down the amount of meat we eat. I have personally done that.
We'll take this question here. I think someone, yes, because it's proximity to the microphone, and then we'll take a couple of questions at the back after that.
Hello, my name's Randall Boydell. I'm an architect and sustainable development consultant. I'm going to play devil's advocate. You said we have difficult choices to make. I'm going to suggest we have choices to make, and they're not necessarily difficult depending on how we frame the argument. And there are actually lots of net wins and win-win situations we get out of this.
Yeah, I mean, there are certainly some no-regret choices that we could easily make, I agree. And there are, undoubtedly some opportunities that we could make the most of this situation with. So there are certain choices we can make relatively easily, but, there are choices about how fast we might do something. And I think that's a very difficult choice. If we have to replace all of our gas heating in this country, how quickly could we do that? That is a very difficult decision to make about how we pay for everyone's gas boilers to be replaced, for example.
I would again challenge you, it's not necessarily difficult. It's how we frame the argument.
Okay, it's expensive, depending on how fast we do it, and whether that cost is what the politicians would like to accept is the difficult question.
So I think we have a couple of questions at the back. So we'll take one on this side first, on your right, and then the next one on the left.
Hello there. Great lecture. Shame you didn't do paleoclimatology. If your clock stops around about Industrial Revolution,
yes.
Okay. Just having spent some time hanging out with the XR mob, going, we're all doomed, it's the end, panic stations, scream and shout. Well, we're all 21, aren't we? The point is, could you tell us a little bit by degrees or 1.5 degrees here or there, what effect we are to expect to see on the base of diversity of life? And are we to expect some kind of creeping sterilization? Not a complete sort of Martian Nowhereville dries a bone, but what is going to happen to the variety of life that we depend upon at the moment?
So we can certainly look back into the past, the very deep past, and try and infer some things about what happened in the past. So I think, looking to the future, I think the The most obvious example of issues for ecosystems are the coral reefs, the warm water corals. The Intergovernmental Panel on Climate Change has suggested we will lose almost all of our warm water corals by 2 degrees above pre-industrial levels. We'll have issues in the Arctic if the sea ice continues to melt. Ecosystem changes in the Arctic are also very important. The paleo record also tells us a lot about sea level rise. So we mentioned Greenland, for example. So the last time temperatures were as this warm back in the deep past, we know that sea levels were tens of meters higher than they are today. It may take centuries or millennia to get there, but we could well commit ourselves to that level of sea level rise because that's what we know has happened in the past when we've been at temperatures to similar levels or just above today.
Do we have a question, I think, there?
Hi, thanks for the great talk. It was fascinating to hear how we've actually known about global warming for over 80 years, as you're saying. Also fascinating to see how only in the last couple of years has there really been a kind of a zeitgeist across the population here and across the world around doing something different. I guess it all started with the banning straws campaign. From your perspective, where do you think the average citizen can put their pressure behind? Should it be in engaging with governments and getting our politicians behind this journey, or should it be in engaging with businesses who, you can argue are the predominant polluters in this case and the drivers behind the increase in temperatures?
So I think the answer is everywhere. And I think actually the most important thing we all need to do, I think, is talk about it. Talk about it a lot more. Keep talking about it all the time. Because if then becomes an issue which people vote about, for example, then that is when politicians might start to listen. So if this is an issue you feel very passionate about, talk about it and then make it mention it if a local council candidate comes knocking on the door, or your local European election candidate comes knocking on the door. Mention it as a key issue. So if that's important to you, then you should do that. We should also talk to businesses, and we do that in the research community. We talk to businesses about the risks that are coming and what they might do to respond. I think they're very well aware. The insurance industry is certainly very aware of the risks that we face. What do we do with the fossil fuel companies? They're going to have to make some difficult decisions as well about where their business goes. But no, we have to. There's no magic bullet for any of this, right? There's no magic bullet for solving it. There's no magic bullet for how we motivate any actions that we might want to see. So we have to do everything. Talk to ourselves, each other, businesses, and politicians.
Okay, we'll have one more, I think, question from down here at the front. Well, halfway, not quite the front. Yes, perfect. There we go.
Thanks so much for a fascinating talk. Vedanta Kumar here from BAYS, actually, from government. This is a science question. You showed a map of data points that you had from going back at, I think, at the time of the storm in 1903. Yeah. But I guess to inform, when we talk about adaptation, a lot of the time we focus on developing countries or low-lying countries like Bangladesh, which are going to be hit. To what extent do we have data points for those countries that are more likely to be severely affected?
Mm-hmm. So we are very lucky in the UK that we've had a lot of observations taken, and lots of countries in Africa and Asia are not so lucky that they haven't had the detailed observations taken for as long. There are undoubtedly large archives in every single country in the world of data which hasn't been used. So I've been at various meetings where we've had representatives from all over the world talking about the paper records that they have, for example, which haven't been digitized. Africa, Asia, all over the place. South America as well. So we do have lots of records. We need to make sure that all those records are available as well. That isn't always the case. Data is not always publicly available or even to scientists available. It can often be kept in country, which is another big issue that we face. And that is another issue that we have to address politically and diplomatically and access some of this data to improve our records. So yeah, it often involves talking to local scientists if we want to get access to some of this data. But yeah, there's always more out there.
Okay, I think on that note, that's an excellent point to finish. Thanks very much, Ed, once again. Now, before you go, I have one very important task. I hope the scroll is under here. Yes, here we are. To perform, which you must all witness to make sure that it's all done properly. So this is the scroll which Ed will receive. I'm assured that the money has been transferred to his bank account already. I haven't checked, but he'll no doubt tell us if it hasn't. So Ed, thank you very much and congratulations once again.
Thank you very much. Thank you.
Thank you.
Thank you.